Hi students, in the last video we talked about pigeonhole principle and some basic principles of counting and permutations. So in this video we are going to talk about combinations and related problems. Combinations. See, a combination is an unordered selection of objects. Okay. Unlike in the permutation, here we don't give a importance for order of the selection. It is like a picking a group or subset where there is no importance for order of the selection. Okay, here is the definition. Let R comma n are non-negative integers. A R combination of n objects is a unordered selection of R of n objects. Okay, we have n objects. We want to pick R objects from n objects without giving importance for order as a group. Okay. So that is called OR combination. Okay, let's look at an example. We have three objects in the set S, A, B, C. Now let us see what are all one combinations. One combinations are one element subsets, singleton A, singleton B, singleton C. Two combinations of S are two element subsets A, B, A, C, B, C. Three combinations of S are only one, which is all set A, B, C, and there are no four combinations because we cannot pick four objects from three objects. Of course, there is a one zero combination, which is like an empty set. Now let me introduce a notation here. We read it as n choose R, which represent number of R combinations of n objects. From the previous example, you can see that 3 choose 0 should be 1 because there is only one 0 combination. 3 choose 1 should be 3 because there were 3 1 combinations. 3 choose 2 value should be 3 and 3 choose 3 value should be 1 and 3 choose 4 value should be 0. Okay, that from our previous experience. Now, what about n choose R? So, can we have a nice formula so that we don't have to list every time to get count for R combinations. Next theorem. We actually have a nice relationship between NPR and NCHOOSE-R. Okay, where NPR is what? Number of R permutations of an object. The reason is when you make a R permutation, you have to choose R objects first, then you have to arrange them, right? So if you think about procedure of making R permutation, which can be broken down into sequence of two tasks. Task 1 is choosing R objects. Task 2 is arranging chosen objects in some order. Okay, here we go. Let us be a set of n objects. Each R permutation of S can be made by performing the following procedure, which is broken down into sequence of two tasks. Task 1. Choose R objects from S, which can be done in n choose R ways. Okay. Task 2. Arrange chosen R objects in some order, which can be done in R factorial ways. We know it. So by product rule, this procedure can be done in n choose R into R factorial ways. Okay, so number of R permutations of an object should be n choose R into R factorial. Therefore, NPR equal to n choose R into R factorial. So that should give you n choose R value equal to NPR by R factorial. But we know NPR already n factorial by n minus R factorial by R factorial. This simplified to n factorial by R factorial n minus R factorial. Okay. Example. 25 points are chosen in the plane, out of which 8 points are collinear, and no 3 points come from outside of these 8 points are collinear. Question A. How many lines do they determine? We know that every 2 points in a plane decide unique line, right? So for every two combination of these 25 points, there should be a line. But any two combination of points that come from these 8 collinear points gives the same line. So the total lines that we get from these 25 points is 25 choose 2 minus 8 choose 2 plus 1. So the answer for A is 25 choose 2 minus 8 choose 2 plus 1. Okay. Okay, question B. How many triangles do they determine? We know that 3 points in a plane form a triangle if and only if they are not collinear, right? Okay. So not every 3 combination of these 25 points going to form a triangle because some of them happen to be collinear. Okay. Now question is, which 3 combination will form a triangle? Which 3 combination do not form a triangle? It is given that no 3 points come from outside these 8 points are collinear. So only time a 3 combination will form a collinear points if all 3 come from this 8 point. So out of 25 choose 3 combination, 8 choose 3 combination going to be collinear. So there are total 25 choose 3 combinations in which 8 choose 3 combination will not form a triangle. So answer going to be 25 choose 3 minus 8 choose 3. Okay, this many triangles, these 25 points will decide. Okay, next problem. How many binary strings are there of length n that has exactly r1s? So remaining n minus r zeros. So we are going to see these binary strings of length n with r1s as permutations of n objects in which r1s are alike, n minus r zeros alike. Okay, so that means they are like a permutation with constant repetitions. Okay, now here we are interested in permutations of n objects in which r1s alike and n minus r zeros alike. And how many such permutations are there? N factorial by r factorial n minus r factorial. That is nothing but n choose r. Okay, so therefore the number of binary strings of length n that has exactly r1 is n choose r. Okay, please keep in mind. Okay, combinations with repetition. What do we mean by combinations with repetition? Let me show you an example. Here we have a big box of Cadbury gems of 4 colors: red, green, blue, purple. Enough number in each color. Okay, say if you go and grab 6 gems for yourself, question of interest is how many different combinations you can get. Here it won't make sense if I ask you which red gems you got. Rather, I should ask you how many red gems you got. Because gems of same color are identical. We cannot differentiate them. Fine. Now, let's do some simulations. Let's get some 10 sample and observe these combinations. Okay. Let's see if we can make something out of it. Here we go. Okay. There are 10 samples. In first sample, 1 red, 1 green, 1 blue, 3 purple we got. In second sample, 1 red, 2 green, 3 blue, no purple. In third sample, 1 red, 2 green, 2 blue, 1 purple. In fourth sample, no red, no green, 4 blue, 2 purple, and so on, as you can see. Here, as we are interested in only number of jumps in each color, so let's write that information here. Okay, in first sample, we got 1 red, 1 green, 1 blue, 3 purple. So next to the first sample, I wrote 1, 1, 1, 3, which represent 1 red, 1 green, 1 blue, 3 purple. Similarly, next to second sample, we have 1, 2, 3, 0, which means 1 red, 2 green, 3 blue, 0 purple, and so on. Okay, so here let's denote x1 number of red gems, x2 number of green, x3 number of blue, x4 number of purple. Then we can observe that this x1, x2, x3, x4 satisfying this equation. x1 plus x2 plus x3 plus x4 equals 6. Okay, so we can see the 4 tuple x1, x2, x3, x4 as non-negative integer solution of x1 plus x2 plus x3 plus x4 equal to 6 equation. Here in this equation, the 6 represent number of gems we are picking, the 4 represent number of colors available. Okay, fine. So there is a one-to-one correspondence between these combinations and non-negative integer solutions of this equation. Okay, so for given combination, I can give you solution for this equation. For given solution of this equation, I can produce the corresponding combination. Okay, here the general problem going to be counting number of non-negative integer solution of this equation x1 plus x2 plus x3 plus x4 equal to 6. Okay, now how do we count number of solution of this equation? Fine. Now what we do, in each combination, let's separate them into 4 groups because there are 4 colors, right? Red group, green group, blue group, purple group. Okay, so to separate them, I'm going to need 3 separators. Okay, I'm going to use 1 as separator. I want 4 groups, right? For that I need 3 separators. I'm going to use 3 ones, and the number of zeros you see equal to number of gems we pick. Okay, here left side of the first one we have a 1 0 which is corresponding to red group. Okay, 1 red, there is a 1 red gem, so we have 1 0. Between first one and second one, I have a 1 0 which is corresponding to green group. Okay, between second one and third one, there is a 1 blue which corresponding to blue group. There is a 1. Right side of the third one, we have a 3 zeros which corresponding to purple group. There are 3 purple gems in the first sample. Next also there is a 1 red, so left side of the first one we have a 1 red 0. So between first 2 ones we have a 2 green zeros because there are 2 green gems, and between second and third one there are 3 blue zeros because there are 3 blue gems. Right side of the third one there is no 0 because there is no purple gem here. Okay, I hope you got the idea. See, for each combination, let's do this encoding. Can you see? Here we can observe something. Each binary string is of length 9 with exactly 3 ones. Okay, and in fact, for any given combination, I can produce binary string of length 9 with 3 ones. For given any binary string of length 9 with exactly 3 ones, there is a corresponding combination we can produce. So there is a bisection between these combinations we can get and binary string of length 9 with 3 ones. Okay, but we know how to count binary strings of length 9 with 3 ones. Okay, which is 9 choose 3. Okay, the number of binary strings of length 9 with exactly 3 ones is 9 choose 3. Okay, so let me express this 9 choose 3 in terms of number of gems we are picking and number of colors of the gems that are available. Okay. So 9 choose 3. The 9 I'm going to see as 6 plus 4 minus 1, 3, 4 minus 1. So 6 plus 4 minus 1, choose 4 minus 1. Okay. The number of zeros we are using exactly equal to number of gems we are grabbing. Number of separators is 1 less than number of colors available. Okay. If we have 5 colors, we would have used 4 separators. If there are 6 colors, you would have used 5 separators. If there are R colors, we would have used R minus 1 separators. That means ones. Okay. The number of zeros will be exactly same as number of gems we are grabbing here. Okay. So these combinations with repetition recognized as binary strings of length 9 with exactly 3 ones. Okay. Now let's generalize this. Generalization theorem. Let n comma r are non-negative integers. The number of non-negative integer solutions of the equation x1 plus x2 plus so on xr equal to n is n plus r minus 1. Choose r minus 1. Here you can think like we have a r colored gems in the box and we are grabbing n gems. Then the number of combinations we can get is going to be n plus r minus 1. Choose r minus 1. Because each combination can be recognized as non-negative integer solution of this equation and each solution can be mapped to binary string of length n plus r minus 1 with exactly r minus 1 ones. Here is the mapping. Mapping from x1, x2, so on xr to binary string of length n plus r minus 1 with r minus 1 ones exactly. So we have a bijection between non-negative integer solutions of x1 plus x2 plus so on xr equal to n2 binary string of length n plus r minus 1 with exactly r minus 1 ones. And we know that number of binary strings of length n plus r minus 1 with r minus 1 ones is n plus r minus 1. Choose r minus 1. Therefore, by pattern recognition, the number of non-negative integer solutions of the equation x1 plus x2 plus so on xr equal to n is n plus r minus 1. Choose r minus 1. Okay. Okay. Corollary. N comma r are non-negative integers with r less than or equal to n. Then the number of positive integer solutions of equation x1 plus x2 plus xr equal to n is n minus 1. Choose r minus 1. Earlier we were talking about non-negative integer solution. That means each xi should be greater than or equal to 0. It could be 0 or some positive. But here each xi should be positive. Okay, fine. Now what we do? Okay, let us take SC set of all positive integer solution of this equation. See, each xi is positive. We are precisely interested in number of elements in S, right? Okay. Now what we do, let us take this transformation. Let me introduce new variable yi which equal to xi minus 1. So whenever xi positive, yi will be non-negative if and only if. Okay. That means x1 plus x2 plus xr equal to n if and only if y1 plus y2 plus yr equal to n minus r. Simple. From this relation, xi going to be yi plus 1. If you plug it here, y1 plus 1, y2 plus 1 and so on, yr plus 1 equal to n. That implies y1 plus y2 plus so on yr plus r equal to n, because 1 plus 1 plus 1 r times. If you take r that side, y1 plus y2 plus so on yr equal to n minus r. That's why whenever with this relation whenever x1 plus x2 plus xr equal to n, you have y1 plus y2 plus yr equal to n minus r. Now, let me look at t, which is non-negative integer solution of this equation. Y1 plus y2 plus yr equal to n minus r, where y's are non-negative. But we know how to count non-negative integer solution of equation. Here, in place of n, we have n minus r, right? So number of elements in T going to be n minus r plus r minus 1. Choose r minus 1 using the previous theorem. In place of n, we have n minus r. So n minus r plus r minus 1. Choose r minus 1. Here r cancel. You will end up with n minus 1. Choose r minus 1. Now we can see bijection between s and t. This is the bijection. Okay. x1, x2, xr map to x1 minus 1, x2 minus 1, xr minus 1, which is nothing but y1, y2, yr. So clearly we see bijection between s and t. Therefore, the number of elements in s should be same as number of elements in t, which is n minus 1. Choose r minus 1. Okay. Example. An investor has $20,000 to invest among 4 possible investments. Each investment must be in units of $1,000. Question A. If the total $20,000 is to be invested, how many different investment strategies are possible? Okay. Here, let xi equal to number of $1,000 invested in investment I, for I equal to 1, 2, 3, 4. Okay. So here each xi is non-negative. If the total 20,000 to be invested, then x1 plus x2 plus x3 plus x4 must add up to 20. Okay. So each investment strategy is like a non-negative integer solution of this equation. But we know how to count non-negative integer solution of this equation. The answer is 20 plus 4 minus 1. Choose 4 minus 1, which is 23. Choose 3. So this is the answer to the question A. Question B. What if not all the money need to be invested? So in this case, there may be some leftover money. Now let's introduce new variable. Let x5 equal to leftover money in $1,000 in $1,000 units. Okay, so it is again non-negative. So if he wants, he can keep some money or he can invest all. So now in this case, x1 plus x2 plus x3, this is the solution to A. Solution to B going to be x1 plus x2 plus x3 plus x4 plus x5. Invested money plus leftover money should add up to 20. Again same, each xi is non-negative. So again here non-negative integer solution of this equation. So this time here r equal to 5, n equal 20. So 20 plus 5 minus 1, choose 5 minus 1. So answer going to be 24. Choose 4. C. What if investor must keep some positive amount as well as invest some positive amount in each 4 investments? This is going to be exercise. I hope you can do this exercise. Okay. Now let us get back to the problem that made us study combinatorics for probability. Here we go. A communication system is to consist of n seemingly identical antennas that are to be lined up in linear order. The resulting system will then be able to receive all incoming signal and will be called functional as long as no two consecutive antennas are defective. If it turns out that exactly m of n antennas are defective, what is the probability that resulting system being functional? Okay, let us denote defective antenna by 0, non-defective by 1. Then each possible system configuration can be seen as binary string of length n with m zeros and n minus m ones. That is nothing but permutation of n objects in which m zeros are alike, n minus m ones are alike. Okay, we know how to count such a permutation. So total possible system configurations, total possible configurations going to be equal to the number of permutations of n objects in which m zeros are alike, n minus m ones are alike. We know how to count such a permutations. Answer is n factorial by m factorial n minus m factorial. This is nothing but n choose m. So this many total possible configurations are there if you want to list them. Okay, our original problem we started n equal to 50, m equal to 20, right? That means 50 choose 20 possible configurations are there. Okay, let me tell you how big this number is. Okay, 50 choose 20 value 471291224396. You know what? You don't have this many milliseconds in your life. So obviously you cannot list them. Okay? So that's why I said it's not feasible to list all possible configurations to find out the probability of that problem. Okay, anyway. Now we know there are n choose m total possible configurations, out of which how many of them actually result in functional systems. A system is functional if and only if there are no two consecutive defectives. That means we should not have a two consecutive zeros in binary string of length n with m zeros and n minus m ones. Okay, now how many such a binary strings are there? Let's try to see how many we can make them. Okay, so what we do to get the count, what I'm going to do, let me list out all zeros first in linear order like this. Okay, you have m zeros, right? You put like this. Okay, now these are m zeros. Then immediately I see m plus 1 spots. Here is 1, here is 1, here is 1, 1, 2, 3, 4, and so on. mth spot, m plus 1 spot. Okay, to make a system configuration, we need to throw remaining n minus m ones in these spots. But we want to throw in a way the resulting system going to be functional. For that, let's say I'm throwing x1 ones here, x2 ones here, x3 ones here, so on, xm ones here, here xm plus 1. Okay, then x1 plus x2 plus so on, xm plus 1 should be number of ones we have, that is n minus m. And if you want your system to be functional, make sure x2 positive, x3 positive, so on, xm positive. Because between any two zeros, there should be at least one 1, right? And there is no condition on x1 and xm plus 1. They can be non-negative. Okay, here x1 should be non-negative and xm plus 1 should be non-negative, but x2 should be positive, x3 should be positive, so on, xm should be positive. Okay, now we are looking for solutions of this equation where x1 non-negative, x2 positive, x3 positive, so on, xm positive and xm plus 1 non-negative. Now let's convert the original equation so that we look for positive integer solution of equation. Okay, let me take the transformation y1 equal to x1 plus 1 so that it is positive. Now, y2 going to be same as x2, y3 going to be same as x3, so on, ym going to be same as xm, but ym plus 1 again going to be xm plus 1 plus 1. Now you see y1 equal to x1 plus 1 means x1 going to be y1 minus 1 and x2 going to be same as y2 and x3 going to be same as y3, so on, xm going to be same as ym, but xm plus 1 going to be ym plus 1 minus 1. Let's convert this equation. Now x1 I'm going to replace with y1 minus 1 plus y2 plus y3 plus so on, ym plus 1 minus 1 equal to n minus m. Now this minus 1 minus 2, let's take that side, then equation become y1 plus y2 plus so on, ym plus 1 equal to n minus m plus 2. Here each yi is positive. Now enough to look for positive integer solution of this equation. Now we know how to count positive integer solutions for equation. So the number of positive integer solutions, let's say this one, positive integer solution of going to be n minus m plus 2 minus 1, choose m plus 1 minus 1. Okay, this is going to be n minus m plus 1, choose m. Okay, so this many systems are going to be result in functional systems out of n choose m. So therefore the probability going to be what? n minus m plus 1 choose m by n choose m. Okay, so this is the probability we are looking for. Okay, next, combinatorial proof. A combinatorial proof of an identity is a proof that uses counting argument to prove that both sides of identity count the same objects but in different ways. Many identities involving binomial coefficients can be proved using combinatorial proofs. Okay. Problem. Prove that n choose r equal to n choose n minus r. Here we are to give combinatorial proof. So algebraic proof going to be simple. If all you need to do, just write n choose r formula, you will see that left hand side same as right hand side. That is boring proof. Here we want to give combinatorial proof. Okay. So we want to come up with some counting argument that says that left hand side, right hand side, same thing. Let's say you have n objects, you want to select r objects. Whenever you are selecting r objects, you are also rejecting n minus r objects. So there is a one-to-one correspondence between the selections and rejections. So the selection is nothing but R combination, rejection is nothing but N minus R combination. So that's why number of R combinations of N objects should be same as number of N minus R combinations of N objects. Okay, here we go. Let us be the set with the N elements. Let me consider script A1 is all subsets of S with size R. They are nothing but R combinations of S. Script A2 consisting of all subsets of S with size n minus R. They are nothing but n minus R combinations of S. So obviously the number of elements in script A1 going to be n choose R. Number of elements in script A2 going to be n choose n minus R. We can clearly see that there is a bijection between the script A1 to script A2. Here is a mapping. A map to A complement. Because whenever A having R elements, A complement will have n minus R elements. So this is a well-defined mapping. It's going to be a bijection. That's why by pattern recognition technique, the number of elements in script A1 should be same as number of elements in script A2. Hence, n choose are same as n choose n minus R. Okay, Pascal identity. Theorem, let n and r be positive integers with n greater than or equal to r, then n choose r is going to be same as n minus 1 choose r minus 1 plus n minus 1 choose r. Okay, let me give an intuition here. Here we want to come up with combinatorial proof, right? Okay, let's say we have a class with n students and we want to select group of r students. How many groups are there? N choose R, right? Now, these groups we are going to classify two types. Groups with CR and groups without CR. The number of groups with CR will be N minus 1 choose R minus 1. The number of groups without CR will be N minus 1 choose R. Okay, so that's why the total number of groups going to be number of groups with CR plus number of groups without CR. That's why we have n choose R equal to n minus 1 choose R minus 1 plus n minus 1 choose R. Here is the proof. Consider a class S with n students and let us fix a student here CR. Script A consisting of all groups with size R. So therefore, the number of elements in script A going to be n choose R. Script A1 consisting of all groups of size R with CR. So the number of elements in A1 going to be n minus 1 choose R minus 1 because we are selecting CR in one choose one ways, then remaining R minus 1 we are selecting from remaining n minus 1 students. That's why 1 choose 1 into n minus 1 choose R minus 1, so which will give you n minus 1 choose R minus 1. Next, now script A2 consisting of all groups of size R without CR. And number of elements in script A2 going to be n minus 1 choose R because we are rejecting CR, so we are not selecting him 1 choose 0. From remaining n minus 1, we are selecting R people. So 1 choose 0 into n minus 1 choose R, it's going to be n minus 1 choose R. So here you can see that the total groups of size R is union of groups of size R with CR and groups of size R without CR. So therefore, and there is no overlapping here. By some rule, the number of elements in script A going to be number of elements in script A1 plus number of elements in script A2. Hence, we have n choose R equal to n minus 1 choose R minus 1 plus n minus 1 choose R. This is the Pascal identity. Note here, this identity together with initial condition n choose 0 equal to 1 and n choose n equal to 1 can be used in the computation of binomial coefficient recursively. The good thing here, there are no factorials involved, there are no multiplications involved. only additions. Okay, in this computation you are using only additions. Additions are in some sense cheap operations for computer. Okay, and as far as computers are concerned, the additions are cheap operation than multiplication. Okay, okay, let's look at the implementation. See, using memoization technique, this algorithm can be implemented very efficiently. Let me run it. Let's, yeah, default 6 choose 2. 6 choose 2 value 15 we know. Let's check for others. See, it's computing very fast. Okay. See, I'm computing, 1000 choose. So, and n choose r equal to 0 if r is bigger than n, right? That's why if I take, n is 713, r is 854, it should be 0. Okay, fine. Okay, Wanderman's identity. Let m comma n and r be non-negative integers with r less than or equal to minimum of m comma n. Then m plus n choose r equal to summation k equal 0 to r m choose k into n choose r minus k. This is a true identity and we want to come up with combinatorial proof. Okay. Let us say we have a class with m boys and n girls and we want to select a group of r students. How many groups are possible? M plus n choose r, right? Now let's classify these group into r plus 1 types. Okay, where type k going to have a k boys, so r minus k girls. Here k vary from 0 to r. For example, type 0 consisting of 0 boys or girls. Type 1 consisting of 1 boy or minus 1 girls. Type 2 consisting of 2 boys or minus 2 girls. So on. Type R consisting of R boys and 0 girls. Like that. Okay. So here the total number of groups should be equal to the number of groups of type 0 plus number of groups of type 1 plus number of groups of type 2 plus so on number of groups of type R. This is an idea. Okay. Proof. Let a class S having m boys and n girls and we select a group of R students. Let's say script A consisting of all possible groups of size R. So the number of elements in script A are going to be m plus n choose R. Then script AK consisting of all groups of type K. All groups of size R with K boys in it. So remaining R minus K should be girls. So the number of elements in script AK going to be m choose k into n choose r minus k. First you select k boys from m boys and remaining r minus k students should come from n girls. So that's why m choose k into n choose r minus k. This is going to be number of elements in script AK, which is size of type k group. Okay, here k vary from 0 to r. Here immediately we can see that the script A equal to union of this script AK where k varies from 0 to r and there is no overlapping here. So by some rule the number of elements in script A are going to be summation k equal 0 to r number of elements in script AK. Okay, here we already see here the number of elements in script A going to be m plus n choose r, right? and also the right hand side summation k equal 0 to r, number of elements in script ak is m choose k into n choose r minus k, right? So this is the Vandermon's identity. Hence, so we have m plus n choose r equal to summation k equal to 0 to r m choose k into n choose r minus k. Okay, and we have a corollary here. Okay, in the Vandermon's identity, if you take m equal to n and r equal to n, that means we have n boys and n girls and we are selecting n students. Okay, in that case, the Vandermon's identity going to be n plus n choose n. That means the left hand side going to be 2n choose n. Okay, the right hand side of the Vandermon's identity going to be k equal to 0 to r, but r is going to be n, right? So k equal 0 to n, m choose k, but m is also n. So n choose k into n choose r minus k, but r is n, so n choose n minus k. Now we know that n choose n minus k is same as n choose k. That's why we have this one. Summation k equal 0 to n choose k square. This is the right hand side. The left hand side is 2n choose n. Simply straightforward application of Vandermon's identity, where you take m equal to n, r equal to n. That means we have an equal number of boys and girls. Okay, the class having size 2n, in which n boys and girls, and you are picking half students, n students. Okay. Okay. Prove that if n and k are integers with 1 less than or equal to k less than or equal to n, then k into n choose k equal to n into n minus 1 choose k minus 1. Okay, let's give a combinatorial proof here. Let's say we have a class of n students and we want to select a group of size k and one representative for that group. Let's do it in two ways. Okay, so that we get a two different expression but both counting the same objects, right? First way is, first select the group of size k from whole class and pick the representative from selection. Okay, so first you pick group of size k, that can be done n choose k ways. Then you pick one representative from selected k people, that can be done in k choose one ways. So this process can be done k into n choose k ways. Second way is, first you pick representative from whole class, then form a remaining group. Okay, first you pick representative from whole class. This can be done n choose one ways, then form remaining group, and remaining group from remaining n minus 1 students. Okay, so with this can be done n minus 1 choose k minus 1 ways. Okay, so this will give you n into n minus 1 choose k minus 1. So as you can see, both counting the same object, so we must have k into n choose k equal to n into n minus 1 choose k minus 1. Okay, prove that summation k equal to 1 to n, k into n choose k equal to n into 2 to the power of n minus 1. Okay, let's give a combinatorial proof here. Let's say we have a class of n students and we want to select a group and one representative for that group. Here I'm not mentioning group size. It could be any size from 1 to n. Okay. We can do it in two ways. First way, we select a representative, then we form a remaining group. Okay, so from whole class you pick one representative in n choose one ways, then you pick remaining group. Remaining n minus 1 people are there, right? You can pick any subset. Already you picked one representative, right? Remaining group can be empty also, because this one person also can form a group of size 1. Okay, so first you select one representative from whole class, that can be done in n choose one ways. Then you pick a subset from remaining n minus 1 people, so that can be done in 2 power n minus 1 ways. So therefore in this way you can see that this process can be done n choose 1 into 2 power n minus 1 ways, that will give you n into 2 to the power of n minus 1. Now, second way, first you select a group of size k. Here the k could be either 1 or 2 or 3 or so on up to n. Okay, so if you select a group of size k, that can be done n choose k ways. From that selection, you have to pick one representative. Okay, but now here you can apply some rule, because here size k can be 1 or 2 or 3 or so on n. Here k can vary from 1 to n. Okay, so this will give you summation k equal to 1 to n k into n choose k. Okay, so but both are counting the same object, that's why we must have this. So summation k into n choose k equal to n into 2 to the power of n minus 1. Okay. Okay. Say a person has 3 children and he got 10 chocolates, all different brand for them. He wants to distribute in a way so that younger one receives 5 chocolates and middle one receives 3 chocolates and elder one receives only 2 chocolates. So question of interest is, how many ways can you distribute them? Simple. This process of distributing these chocolates can be broken down into sequence of 3 tasks. So here task 1 is distributing 5 chocolates to younger child from 10 chocolates, which can be done in 10 choose 5 ways. Task 2 is distributing 3 chocolates to middle child from remaining 5. This can be done in 5 choose 3 ways. Task 3 is distributing 2 chocolates to elder child from remaining 2 chocolates, which can be done in 2 choose 2 ways. So by product rule, this process can be done in 10 choose 5 into 5 choose 3 into 2 choose 2 ways, which gets simplified to 10 factorial by 5 factorial, 3 factorial, 2 factorial. Okay. Theorem. Let n be a positive integer and n1, n2, nk be positive integers with n1 plus n2 plus so on nk equal to n. Then the number of ways to distribute set of n objects into k labeled boxes b1, b2, so on bk, in which box I contain ni objects for I equal to 1 to k equals to n factorial by n1 factorial, n2 factorial, so on nk factorial. Okay, the proof is simple, just like the previous problem. Okay, so n choose n1 into n minus n1 choose n2 and so on. This whole thing gets simplified to n factorial by n1 factorial, n2 factorial, so on nk factorial. Okay, here you have to be careful with the labeled box condition. If it is not labeled, you have to be careful. So we'll see some example, because it may create a problem when you are dealing with unlabeled boxes. Okay. Okay. Question 1. How many ways can we divide 7 objects into 3 labeled groups with the labels G1, G2 and G3 with the sizes 2, 2, 3 respectively? That means, how many ways we can divide these 7 objects into these 3 groups. So G1 contains 2 objects, G2 contains 2 objects, and G3 contains 3 objects. Okay. The answer is 7 factorial by 2 factorial, 2 factorial, 3 factorial by above theorem. Okay, fine. Now, question 2. How many ways can we divide 7 objects into 3 unlabeled groups with sizes 2, 2, 3 respectively? Okay, so can I still say answer is 7 factorial by 2 factorial, 2 factorial, 3 factorial? No, we have a problem here. Let's say our 7 objects are 1, 2, 3, 4, 5, 6, 7. Okay. Now, let me give out 2 examples in the labeled case. Okay. Let's say, let me list out 2 examples with a labeled case. Then let me remove the label. Then see what happens. Here, these 2 are 2 divisions of the 7 objects into the 3 groups of size 2, 2, 3. Okay. Now, these 2 are going to be counted differently here. Okay, obviously. Okay, here because G1 contain 1 and 2, here G1 contain 3 and 4. They must be different. They are different in this count also. But if you remove labels, but these 2 are going to be same. You cannot differentiate between these 2 once labels are removed. So we are going to have a overcount here. Okay, so in fact each is overcounted exactly 2 factorial times. This 2 factorial is the number of ways we can shuffle groups among the groups of the same size. Here only 2 groups of same size, so they can be shuffled among themselves in 2 factorial ways. All will result in same divisions in the case of unlabeled groups. Okay, so we can fix this by dividing by 2 factorial. So therefore the correct answer going to be, after fix, you just have to divide this count by 2 factorial, so that will give you this. Okay, next question 3. How many ways can we divide 9 objects into 3 unlabeled groups of size 2, 3, 4? Note that all sizes are different. In earlier, there were 2 sizes same, but here all sizes are different. So what is the answer here? Answer going to be simply this. 9 factorial by 2 factorial, 3 factorial, 4 factorial. Because though I said unlabeled, they implicitly got labeled with their sizes. Okay, I can say like a label group size 2, group size 3, group size 4. Okay, they are going to be labels. There is no ambiguity. But earlier there were 2 groups of size 2. So I can't label with the sizes because there is an ambiguity. Here there is no ambiguity, so they implicitly got labeled, so there is no problem like we had earlier. So if all sizes are different, whether labeled or unlabeled, answer will be same. If some sizes are same, then you have to fix the answer. Now let us say we have a 16 objects here. Now we want to divide them into 6 groups of size 2, 2, 2, 3, 3 and 4. Unlabeled groups, okay? We want to divide them into 6 unlabeled groups of sizes 2, 2, 2 and 3, 3 and 4. Okay? So we know that answer is not going to be this, right? 16 factorial by 2 factorial, 2 factorial, 2 factorial, 3 factorial, 3 factorial, 4 factorial. This is not going to be the answer, right? Because we have a problem when we have the same sizes in the case of unlabeled groups. Okay. Now we have to fix it by dividing by something. That something is over count of each division in this count, right? So how to get that over count? I told you that in the labeled case, if we shuffle groups among the groups of the same sizes, the corresponding unlabeled divisions will be same, right? Okay, so that would be the over count. So here there are three groups of same size too, so they can be shuffled among themselves in three factorial ways. There are two groups of the same size 3, they can be shuffled among themselves in two factorial ways. There is a one group of size 4 can be shuffled among itself in one factorial ways. Okay, so this is going to be over count for each division in the unlabeled case. So to fix that, we need to divide by this 3 factorial, 2 factorial times 1 factorial. So answer going to be 16 factorial by 3 factorial, 2 factorial, 1 factorial into 2 factorial, 2 factorial, 2 factorial, 3 factorial, 3 factorial, 4 factorial. Okay. So this is how you fix it in the case of unlabeled groups having same sizes, right? Now let me state more general version here. Just try to understand intuitively. Okay. Theorem: let n be a positive integer and n1, n2, so on nk be positive integers with n1 plus n2 plus so on nk equal to n. Okay, there are k sizes here. Total number of objects going to be n1 plus n2 plus so on nk equal to n. Okay, now the number of ways to distribute n objects into k unlabeled boxes where box I contain ni objects for I equal to 1 to k. Okay, here k1 of the sizes are same, k2 of the sizes are same, and kr of the sizes are same where k1 plus k2 plus kr equal to k. Okay, see there are k sizes in which K1 are same size, K2 are same size, Kr are same size, then total add up to K, total sizes, right? Fine. If I compare with the previous example, here K1 going to be 3, K2 going to be 2, K3 going to be 1. Here K1 plus K2 plus K3 equal to what? 3 plus 2 plus 1 equal to 6. That 6 is what? K. Here K is what? Sizes. How many sizes? 1, 2, 3, 4, 5, 6. Here K equal to 6 in this example. Okay? Fine. Okay? So now the general 6 is going to be this. Okay? The answer is going to be n factorial by k1 factorial, k2 factorial, so on kr factorial into n1 factorial, n2 factorial, so on nk factorial. So this is going to be the fixed answer for general case. Let me clear this. Next. Here is the exercise. How many ways can we divide mn people into m groups of equal size? No labels. Okay. So m groups of equal size means what should be that equal size? N, right? So m groups means we have sizes n, so on n. How many? M. So now try to apply above theorem. So here I'll tell you the sizes k equal to m here, and r is going to be 1 because r is like a number of different sizes, right? There is only one size here, n, so r equal to 1. So, and sum of this k should be equal to k, but there is only one k1 here. K1 must be equal to k, which is m. Now try to apply above theorem to answer this question. Okay, thank you.